The last section, measures of center, is supposed to give you an idea of how to figure out what a typical value of the data set would be. This section, measures of variation or measures of spread, is supposed to give you an idea of how spread out a data set is. And then there are different ways of computing that. But suppose we have two sets of exam scores. So these two here, both means and both medians are 75. But the second one is clearly more spread out than the first one. But if you just looked at a measure of center, you wouldn't see that, right? Like if you had a summary and that was all that you had there, that's not what you're going to be able to see. You would just see the 75. So what measures of variation are for are ways of quantifying how spread out a data set is. And there are a few different options here. The first one, which is not great, actually, the other ones that we're going to talk about are a lot better, but this is the best starting point. So the range, it's the difference between the extreme values, so between the max and the min. Clearly going to be sensitive to extreme values, typically not very useful unless you're going to use it for an approximation. And we'll see that toward the end of this section. There's a place where you use it, where you use the range divided by 4 as an approximation. And that is actually the most useful time for this. And that's really the only place you would probably see it. But here, and this is kind of illustrating just, if you use extreme values, this is what's going to happen every once in a while. So the two data sets are the same, except this one has a 105 as the largest value, and this one has a 10. So then if you figure out the range where it's max minus min, this one's going to be 105 minus 1, which is 104. This one's 10 minus 1, which is 9. So those are vastly different, and those data sets are almost exactly the same. So that's why the range, just as a measure of variation by itself, is probably not the greatest thing to use. So instead of using the range, what if we wanted to figure out the average deviation from the mean? So then notationally, if x is a value in the data set, then a deviation would be x minus x bar, right? Since x bar is the mean. And it seems like you could compute the deviation from every value in the data set, divide by the sample size, then that would give you the average deviation, but that doesn't quite work because what will happen every single time is that no matter what data set you have, so like it works for this example here, but it will work for everything, you will get 0 for the sum of your deviations. And it's because of the way that the mean is computed. Basically, what you end up doing, it's almost like you're doing like inverse operations. And you're always going to get 0. So this isn't really going to work, right? If we're going to get 0 every time, then that doesn't give us any information about the data set if every single data set gives you a 0. So what about if instead of using just regular old deviations, what if we use their absolute value? And then we just said, okay, well, this is how far away this number is from the mean. And then you're not going to get these negatives like how these first three are negative, right? Then you just have like 13.2, since that's the absolute value of negative 13.2 and so forth. And sometimes that is used in certain cases, but because calculus was used to derive some of the advanced statistical methods, the thing that ends up being used is squaring, which will also give you all positive values, right? Like you square like negative 3 squared is positive 9, that kind of thing. So you're still going to get all positive values, and this is just another way of doing it. And it fits in with how calculus was used to kind of prove some of the more advanced stuff. So, all right, variance. This involves the squares of the deviations. So it's the value you get when you square the individual deviations, add them together, and divide by the total number of deviations. Okay? So it would be the average squared deviation, right? But the issue here is that if you're squaring everything, you're also going to square the units. So then sometimes that gives you a measure of spread that's really awkward because it's sort of hard to conceive of. Like what if your data set is all about weight? So either way, either using English measure where it's in pounds or using metric where it's in kilograms, then the variance is going to have the units squared, so it would be in square pounds or square kilograms. And if you're thinking, I don't know what that means, then we're all in the same boat. I don't think anybody knows what that means. So that's why this doesn't quite work the way that you would want it to, because you think, well, by itself, I don't know what that tells me, because I don't know what square pounds are, right? Like, that's not a thing that exists physically, right? It's just pounds. That's one-dimensional. It's not two-dimensional. All right, well then, what if we took the square root? Because then if we took the square root of the variance, we'd also take the square root of the units of the variance, and then we'd be back to regular units. We'd be back to pounds or back to kilograms. So that's what the standard deviation is. So really the standard deviation is just the square root of the variance. If you were going to grind out the computation by hand, you would actually do that exact thing. You would get the variance first and then take its square root to get the standard deviation. That would give you a measure of the average distance from the mean instead of the average squared distance, since we are taking a square root. And the units are going to match up with the original units, so then that becomes a lot easier to understand by itself, right? If the standard deviation is 3.2 pounds, we go, okay, I know what 3.2 pounds means, right? Rather than square pounds, right? Well, that's one where you go, I don't know about this. But pounds by itself, kilograms by itself, that makes sense, right? Then the way that you would compute the population standard deviation is a little bit different. So this slight difference, it's very slight, but it's important, and we'll see it in a second. It's going to look weird, so I tried to throw a justification in there for why it happens, because it's not the intuitive thing to do, and you'll see why. So here's the notation, first of all. So if you look at the standard deviation notation, it's really just the square root of the variance notation in both cases. Or I guess the other way around, the variance notation is the square of the standard deviation notation. But for population variance and population standard deviation, you use a lowercase Greek letter sigma. That's what that is. That's a lowercase sigma. So the uppercase one kind of looks like a big E, but the lowercase one looks like that. And then I guess you can probably take a guess here that the S stands for standard deviation, which seems like that makes sense to me. But then if the variance is the square of the standard deviation, then it's S squared. Okay. And then the way that you compute them, in both cases, you figure out the variance first and then just take the square root to get the standard deviation. And the numerators are basically the same concept, right? Where this is going to be the sum, right? That's what the capital sigma is. That's a sum of the squared deviations, because the x minus mu, that's the deviation from the population mean, since mu is the population mean, and we're squaring it. So, okay, this is the sum of the squared deviations, and then we're dividing by the population size, right? That's big N. And then here, for the sample standard deviation, you go, okay, well, this has an x bar instead of a mu, and that's because it's a sample standard deviation, so we're looking for the average deviation from the sample mean, not the population mean, so x bar, not mu. But then why are we dividing by little n minus 1? Why aren't we dividing by little n? Right? That's the thing that would make sense if we were going to try to figure out the average squared deviation. So why is it little n minus 1? And that's actually what the rest of this page is about. There is a reason for doing that. What happens is if you divide by little n instead of little n minus 1, what happens is that s squared will consistently underestimate sigma squared. So the sample variance will always be too small, in other words. And that's a biased measurement. Right? If it's always wrong in the same direction, that's biased, right? Like when we talked about sampling methods that would give you biased results, right? If you have like an opinion poll that's biased, the numbers are either always coming in too high or they're always coming in too low, right? And this is a case where if it's underestimating, it's always too low, it's always too small. So that's a biased measurement. That problem is fixed if instead of dividing by n, you divide by n minus 1. Okay, fine, but then why does that work? It works because the computation of s squared is based on x bar, right? Like x bar is in this computation of s squared. But x bar already uses all of the data points that are in your data set, right? Because in order to get x bar, you got to add them all up and divide by n. So because s squared is itself based off of another computation that uses the entire data set, there's this idea of where you lose a degree of freedom, or you have one less free value, and that's kind of what this is about here, where it says if you know what x bar is and you know what n minus 1 of the values in the data set are, you could figure out the missing one, right? Like you could solve for it algebraically, because you could just sub all the numbers in and you'd say, oh, so this unknown one, if we multiply both sides by the sample size and sum all the ones we do know and subtract that from both sides, you'd get the one that was missing. And okay, fine, but then that would mean that there's one value that's not free when x bar is known. So like if you knew what x bar was and you knew all the values except for one, you can always get that last one. And so it's this idea of where you lose a degree of freedom, and so dividing by n minus 1 is going to work better than dividing by n. And later when we talk about the degrees of freedom idea in more detail, which will be when we get into confidence intervals, this is going to show up again. But that's kind of why. And just to have sort of like some sort of justification. I didn't think we needed like the full like proof-based thing. I mean, that's kind of long and it'll look like a whole bunch of symbols, but that's the basic idea. It's this last thing right here. The important part is that when you're getting a sample variance, you've got to divide by n minus 1 instead of n. And that does feel a little bit weird, so I wanted to at least have some kind of justification there. All right, then the next thing, generally less variation is preferable because that usually gives you a more straightforward conclusion, I suppose. So computationally, that would mean that a smaller standard deviation would be ideal. So suppose we're studying the effects of a cold and flu medicine, like it says there, and we want to know how often people should take the medicine, or we want to give like a recommendation, right? So like every 4 hours, every 6 hours, every 12 hours, something like that. So let's say that we had an observational study, and we collected data to see how long it seemed like the medicine worked. And if we had this plot right here, you'd go, all right, it looks like if we said take it every 4 to 6 hours, right? Because here are all the big bars here, right? Only 3 people were under 4. So it looks like if you took it every 4 hours, you have a pretty good chance of avoiding the symptoms, right? Like you'd be able to suppress them. So yeah, 4 to 6 hours looks like it makes sense based on that graph. But what if we got this one? And notice the scaling is different, right? Like 5, 10, 15, 20. Here, there's a lot more variation in that dot plot. So then, like, if you were going to give a recommendation, like, what would it be? Right? Like, there aren't any big bars here, and there's nothing that looks like it's rare, like on the low end, like how here, 1, 2, and 3 don't really have very much. Right? Like, look at this thing, like, where it's all spread out, and think, yeah, that's a tough one. Like, what do you say there? So that's the point, is that if you don't have a lot of variation, usually your conclusion gets more straightforward. It gets a little easier to come up with. And here, if you have a lot of variation, it's hard. Right? It's messier. So that's the whole point of this example on this page. Let's see. Going through the computation. So for the example at the very beginning, where it was the 2 samples of size 3 with the exam scores, this is what the computation looks like. And if you think, this is looking a little bit intense already, the other part that you have to remember is this is with 3 values. Most data sets are going to have way more values than that. So to go through the computation by hand probably is not worth it, usually. You can do it, right? And you can see like there's the n minus 1 in the denominator, and here all the squared deviations are down here. There are those squared deviations. So you can do it by hand, but really this is where calculators and software come in handy. And there is the video for how to do it with StatCrunch where it'll show up with the other summary values, and it's just part of the default setting that's what you're going to get. And that's probably going to be your best bet there. Then, properties of the standard deviation. I was thinking ahead of the empirical rule, but we're still here. All right, so it is supposed to be a measure of the average distance from the mean, right? If variance is average squared distance, then when you take the square root, you get your standard deviation. That would be the average distance. The units match up with the units in the data set, so easy to interpret. You can't have a negative standard deviation, which I guess you could see it from these computations because these are all squares in here, right? You're not going to get any negative numbers out of that when you're squaring values. There is a way to get 0, but in order to get that, all the values in the data set have to be the same. Because in order to get 0, like all these things in parentheses would have to work out to be 0. So every value would have to be equal to the mean. So they'd all have to be exactly the same. So in reality, you wouldn't see that, but in theory, you could get a 0. And then the larger your value is of S, then the more variation you've got. And I guess vice versa, right? The smaller the value of S, the less variation you've got. And then, like when we talked about being resistant or not resistant to extreme values, that factors in here too, because we said the mean was not resistant, so it was a computation that could be heavily affected by outliers. So because the standard deviation computation is based on the mean, then if the standard deviations, or if the mean's affected by outliers, then so is the standard deviation. All right, now to the empirical rule, sometimes called the 68-95-99.7 rule. I suppose the 68-95-99.7 rule sounds like a really long-winded name, but that actually gets all of the information in it that you would probably need too. But usually it's just called the empirical rule. So these 3 bullet points are the whole idea, that if you have a data set that's approximately normal, so approximately bell-shaped, then about 68% of the values in the data set are going to fall within 1 standard deviation of the mean, get about 95% within 2 standard deviations, and about 99.7% within 3 standard deviations. So you can see it like this with the bullet points, or you can see it like this with the picture. So there's the mean in the middle, right? This one's a perfect bell shape, but x minus s is 1 standard deviation below the mean, x plus s is 1 standard deviation above. So within 1 standard deviation would be between x minus s and x plus s. You get about 68% of your data in there. And then if you go 2 standard deviations away, so x minus 2 times the standard deviation up to x plus 2 times the standard deviation, you get about 95% between those 2 numbers. And then about 99.7% within 3. So if you look at those values, like those cutoffs, that's 3 standard deviations below the mean. That's what x bar minus 3s is. And then up here, x bar plus 3s is 3 standard deviations above the mean. Okay, so for an example, where it says that a plumbing company has found the length of time it takes to install a bathtub has a bell-shaped, or approximately normal distribution, with a mean of 140 minutes and a standard deviation of 20. So then, using the empirical rule, about 95% of all bathtub installations will take between some number of minutes and some other number of minutes. We could actually use the picture for this too. So let's see. The mean's 140, so the 140 is actually going to be right here, right? Since that's our mean. And then if the standard deviation is 20, then you'd say, well, then this is going to be 140 minus 20, so that's 120. This up here, the x bar plus s, is 140 plus 20, that's 160, right? And then you go an extra 20 down, that's 100. Extra 20 up is 180. I guess we might as well finish this off. Say that's going to be 80, and then this one over here is going to be 200. Okay, so another way to do this, though, is 95%, right? That is going to be 2 standard deviations according to the empirical rule. So you need to go 2 below and 2 above. So you'd need x bar minus 2 times s, and then x bar plus 2 times s. So you could just substitute in here and say, well, then this would be 140 minus 2 times 20. But 2 times 20 is 40. So this is 140 minus 40, which is 100. And then x bar plus 2s would be 140 plus 2 times 20. So it's going to be 140 plus 40, which is 180. And then I guess I could fill in the blanks, right? I have the numbers between 100 minutes and 180 minutes. And that's basically the idea with the empirical rule. And I mean, I guess you could do it with the 68, you could do it with the 99.7, right? And then you're just going 1 standard deviation for the 68, you're going 3 for the 99.7, that sort of thing. But then, all right, the range rule of thumb for identifying a significant value. Our book and the homework are kind of big on this concept. So this is sort of a big thing here. So what's considered to be unusual or significant? The rule of thumb is it's anything more than 2 standard deviations away from the mean. So that's basically what this says, just with symbols. Right? Significantly low would be values below mu minus 2 sigma. Significantly high would be values above mu plus 2 sigma. So things that are significant or unusual are more than 2 standard deviations away in either direction. And then things that are in between are considered to be not significant, right? So less than 2 standard deviations away in either direction. So for the bathtub installation, if we were looking for, I guess we'll say unusual values. So if I go up, since we did write everything in the picture, so beyond 2 standard deviations, that's out here. So, I mean, even if you just think about, like, most of the curve clearly is between 100 and 180, right? About 95% of it is. And so it's just like this little tail out here and this little tail out here. Those are the unusual ones. So we'd already figured out these numbers, these cutoffs. So 100 was 2 standard deviations below the mean, and 180 is 2 standard deviations above. And that's exactly what you would use here. So going back down here, what would be unusual? Well, for the left tail, like for things that are going to be really fast, like where the amount of time is really short, so less than 100 minutes is unusually fast. All right, since the 100 was mu minus 2 sigma, or I guess here we're using the sample notation, so we had x bar minus 2s, right? And then I guess more than 180 minutes. So more than 180 minutes is unusually slow. And that 180, that is, we weren't using that, we're using the sample notation. So x bar plus 2s. It's that 180. Okay, then another example where we don't have the computation done already, where it says that 40 cookies were sampled and the number of chocolate chips in each was counted, and the mean is 24, the standard deviation of 2.6. So would 30 be considered unusual? Well, that's higher than the mean, right? The mean is 24. So we only have to check the higher end. So the only number that we really have to check is x bar plus 2s, right? X bar minus 2s isn't going to do anything for us because this 30 is on the higher end of the distribution anyway if the mean is 24. So x bar plus 2s is going to be, that'll be 24 plus 2 times 2.6. So that's 24 plus 5.2, which is 29.2. So that's the cutoff on the higher end, where then anything above 29.2 would be considered unusually high. And 30 is bigger than 29.2, right? So 30 is greater than 29.2, which that means it is considered to be unusually high. So all we did in this example, and really here we only had to use half of it, right? You don't need the x bar minus 2s. You can compute that if you want to, but it actually it doesn't help, but it doesn't hurt, I guess. But it's work that you don't have to do. So we just use the upper end because 30 is bigger than 24. But all you have to do to see if you have an unusual value is basically you just have to go 2 standard deviations away and see if that value is farther. If it's farther, it's unusual. If it's closer, it's not unusual. That's pretty much the whole story there. And that is a big thing, like in our book and therefore in the homework, that concept, that range rule of thumb, going 2 standard deviations away. It's a big thing. It has a tendency to show up not just in this section, but also going forward. Here is that thing I was talking about at the very beginning where the range actually shows up. And that's what if you're in a situation where you don't have all of the data but you have the extreme values, then you could, if you could estimate the extreme values, sometimes it's like that too. But then you can estimate the standard deviation, and you do it by taking the range, so max minus min, and then dividing by 4. So with that rat example, the actual sample standard deviation is about 2.313. But let's say hypothetically, if we didn't have all of the original data, but we had the max and the min, then you could estimate the sample standard deviation by saying, okay, well, the range would be max minus min, right? So range over 4, really that's max minus min over 4, but the max is 18.4 and the min is 9.4, and then we're dividing by 4. So the numerator is really just 9, right? So this is 9/4. So it's 2.25. Not bad. A little low compared to 2.313, but considering like if you didn't actually have the data set, but you did have the extreme values, it's not terrible. A lot of times it doesn't undershoot. A lot of times it overshoots. Like if you were trying to estimate GPA or something, and you needed, or you're trying to estimate the distribution of GPA, but you didn't really have a lot to work with, and you just said, well, the lowest possible GPA is 0 and the highest is 4. There you're going to get an estimated standard deviation of 1 because it'll be 4 over 4. The standard deviation there is nowhere near that big. And a lot of times that's what happens. This one happened to work out the other way where the estimate was smaller than the actual sample standard deviation, although that is admittedly not the way that usually goes. At least not in practice. Then the other thing that we can have here, the coefficient of variation. This is the very last thing in this section. So what if you have 2 samples and you want to compare variations? And if the 2 sample means are the same or they're really close together, they're like right on top of each other, then you could just look at the 2 sample standard deviations and you go, oh, well, this one's bigger than this one. So the bigger one, that's coming from the more spread out data set. But what if that's not the case? Then you have to use some kind of relative measure almost, right, where you have to factor in that somehow these values are different. Because what tends to happen is that generally if you have bigger numbers, they tend to be more spread out. Right? Like if your measurements are generally larger values, you tend to have a larger number for the standard deviation. So you got to factor that in somehow. So what you can do is figure out the standard deviation relative to the mean. Usually it's expressed as a percentage. So in order to do that, you just multiply by 100, right? Like the way that you would normally convert a decimal into a percent. It's that. And if you look at what the coefficient of variation is, it's just you take your standard deviation, divide by the mean, and then convert it into a percent by multiplying by 100. Okay, so here, the number of cars sold versus the commission, like those numbers aren't the same size, right? For the number of cars sold, you got a mean of 87, standard deviation of 5. For the commissions, you got a mean of $5,225, standard deviation of $773. So if you look at this and you think, okay, yeah, these numbers, the commission numbers are way bigger. Yeah, that's the idea, right? It's on a totally different scale. Right? Like it's not just in ones. I mean, if it was in ones, no one would ever sell cars, right? Because then the commission would be like $1, right? No one would do that for a living. That would require selling an outrageous number of cars. So yeah, they're scaled totally differently. But we can compare them by figuring out the coefficients of variation. So for sales, what we'd have is that the coefficient of variation is going to be 5 over 87, right? So it's standard deviation divided by mean times 100. And what that would work out to is it's about, let's see, I've got it written down, about 5.7%. Right, so I guess 0.057 or 5.7%. And then the commission, we can do the same thing. So there the coefficient of variation would be 773, our standard deviation, over 5225, which is our mean. And then we're going to multiply that by 100. And what you get there is about 14.8%. So this is a lot bigger, right? 14.8 is a lot bigger than 5.7. And now with these, we can do the direct comparison. So then I guess we can say that since the coefficient of variation, which I'm just going to abbreviate as CV, is higher for commissions, then commissions are more variable, right? Like that's what that's telling you. That whichever one gives you the higher value for the coefficient of variation, those are more variable. They're more spread out relative to how big those values are. So we can say that commissions are more variable than sales. Okay, so that's what you would do if you want to compare two standard deviations from data sets that are clearly different, right? And like it said up above, where if your sample means are pretty close together, then or like right on top of each other, then yeah, you could just look at the two sample standard deviations and kind of be done with it. But when that's not the case, like here where the scaling is way, way different, then that's where we use the coefficient of variation, because essentially that factors in the idea that with bigger values, they're just generally going to be more spread out. But then once you get these, then you could do a direct comparison and you go, yeah, 14.8 is a lot bigger than 5.7, right? About, I guess a little more than 2.5 times as large, right? So you go, yeah, definitely bigger. So commissions are going to be more variable here. And then at the very bottom, it's how you can get the measures of variation in StatCrunch. If you look at this, it's identical to how you get the measures of center. It's the exact same steps because the measures of variation or spread that you may want will show up within like the default setting. And so they all just show up within that table that basically will be your output. And you can see that in the video that's about using StatCrunch. But if you can do one, you can do the other, right? If you can do the measures of center, you can do the measures of variation, because it's basically you go to the same place to get both of them.